looking at independent practice 5.1, these problems were all connected. It's numbers 13 through 15, and they're all related to this little spinner, which I know might be kind of tiny in the video. But they asked first on number 13, what's the probability of getting a multiple of 3? So first thing that's really important is that we recognize on that spinner, all of these little slices, these little pie slices are equally spaced, which means they're equally likely for the spinner to land on. And then the numbers that we have, there's 10 of them. We got 4, 6, 9, 12, 15, 18, 21, 24, 27, and 30. Okay, so the spinner's going to spin and it's going to land in one of those zones. Now they want to know what is the probability of it landing on a multiple of 3. Well, a multiple of 3 are the numbers you get when counting by 3. So 3, 6, 9, so on and so forth. So I want to go through and first find out, well, how many spaces I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It looks like there's a total of 10 spaces. And as I go around here, looks like most of them are multiples of 3. Like all these numbers I highlighted, 6, 9, 12, 15, 18, 21, 24, 27, 30, those are all multiples of 3. The only one that isn't is the 4. So this probability is going to be fairly high. It turns out there are 9 desired locations, 9 favorable locations, 9 slices that are a multiple of 3 out of a total of 10. So that's our probability of landing on a multiple of 3, 9 out of 10. And I would leave it like this, but just so you know, this could be written as 0.9, right? That's the decimal. Or you could write it as the percent, 90%. And if you're not seeing that off the top of your head, right, it's just the division of the fraction to get you there, 9 out of 10, 0.9. Multiply that by 100, or 90%. I almost said 100%, 90%. Okay, then it's asking, okay, what if we spin 30 times? And it stops 20 of those times on a multiple of 3. So this is now experimental probability because we're basing it on data. Experimental probability. And it should be noted maybe up here that this guy was theoretical probability. This is what we expect to happen. This is what should happen. So this one is theoretical probability. I think I'm spelling it right, probability, okay? So this is kind of what should happen, what we expect to happen. This actually did happen. We actually ran trials. They spun 30 times and it stopped on a multiple of 20. So this time, our probability was 20 out of 30 times. Just a little bit, so that's 20 out of 30, which is 2 out of 3. Now, same thing, if we went to the decimal of the fraction, this would be 2 divided by 3. You could, of course, do 20 divided by 30, you get the same thing. So it's about 0.6 repeating. I'm going to go ahead and just put, I'll just keep it so it's exact. I won't have to round it yet. Now, when we put it in percent, we typically will round. So we do times 100. So it's about 66.7, or I'm going to just round it to about 67%. I'm going to squiggle my equal sign so that I know it's approximately. It's about 67%. Okay, so actually quite a bit lower than the theoretical probability. We expected it to land there 9 out of 10 times, 90% of the time, but it actually only landed there about 67% of the time, 2 out of 3 times. Okay. Now the question is then asked, well, why do 13 and 14 have different probabilities? It was the same general idea, landing on a multiple of 3. Well, that comes down to understanding the difference between theoretical probability and experimental probability. Theoretical probability is what should happen. This is what actually does based on data. The experimental probability does not always match the theoretical. It typically will once you've done lots and lots of trials. In fact, we have a law for that in math called the law of large numbers. But 30 may seem like a lot, but it's not really. You'd have to do like several hundred really to get probably more accurately closer to this number. So what happened was when we rolled here, we got a lot more 4s than we anticipated. But that can happen, okay? This is not a guarantee. It's what we expect to happen, okay? So let's get that in some words here. Why do 13 and 14 have experimental probabilities? So I'm just going to abbreviate the theoretical probability, which is from number 13, is what should happen, and that's key. Experimental probability is what actually happens when you run trials. I'm going to switch to a pen. I'm afraid I'm not going to be able to fit it here. The experimental probability will eventually match this, or should eventually match this, but only after you've done lots and lots of trials. You must run, I'm going to put a lot more trials to make it more likely that the experimental probability matches the theoretical. Again, that's called the law of large numbers, but you have to run a lot more, okay? Hope that's helpful and gives you a little bit of an understanding about the difference between theoretical probability and experimental probability. Message me anytime, and I'll see you in class.